Good morning. Now what we're going to do is we are going to take this regression model that we've been using, the general linear model, and we're going to apply it to multiple categories. So we're not just comparing two groups together, right, like the t-test. We're going to compare multiple groups together. We can have 4 or 5. We can have as many groups as we want and test them all simultaneously to see if any one group appears that's the cream of the crop, the one that performs best out of all of them, or if any one performs significantly lower than the others. Okay, and this is what's called the analysis of variance. Now let's jump right into it. So what we're going to do is share my screen, as I always do. I didn't forget this time. Okay, and here I've got some data. What we have is water pressure, okay, in a manufacturing process that creates matted fibers, okay, like a felting process. And we are measuring the tensile strength in newtons per 5 centimeters of a set of dog bones, right? Dog bones that we've made of these felted materials, okay? And we're going to say is, does it matter what pressure I use to create these felted materials? Are the materials stronger at higher pressures, or are they stronger at lower pressures, or is there no difference? If there's no difference, then I might as well use lower pressure. It's going to be cheaper. It's going to use less energy, right? I'm going to spend less on the piping and all those other sorts of things because it doesn't have to be able to withstand that pressure. If there is a difference, then I want to find the group that's the difference. If it's nice and linear, then 200 might be greater than 60. If it's curvilinear, right, where we have some local maximum, maybe 100 or 80 is better than 60, and maybe 120 and 150 and 200 are too high. Okay? So this allows us to optimize. So what we'll do is we're going to put these in a familiar form. I'm going to have so notice this is water pressure and tensile strength, water pressure and tensile strength. I've got 60, 80, and 100 bar for the 3 groups of water pressure here. There's 3 groups of water pressure here, 120, 150, 200 bar. Okay. And so what I'm going to do is I'm going to put all the water pressure into a single column. I'm going to put all the tensile strength into a single column vector. And what that does then, okay, this gives me a vector at this time of my independent variable, water pressure, okay? And it gives me a vector of my continuous outcome, my continuous dependent variable, tensile strength. And what I'll do is I'll regress tensile strength on water pressure. And I could do it using the multiple regression techniques we've done already, right? Putting a column of 1s in front of water pressure and just running the regression. I could do that. But there's a more efficient way of doing it overall in Matlab, the programming. The mathematics behind it's all the same as what we've done before. It's just regression. But there's a more efficient routine, and we'll show you that. So we're just going to take our data, grab that data, and I'm going to put that into Matlab, like I always do. Get a new variable open, drop it in. Okay, I'm going to call this data, maybe. There we go. And now what I'm going to do is I'm going to make I'm going to make a vector for my independent variable and a vector for my dependent variable, and we'll use those in the function. So I'm going to say, is it pressure? This is going to be equal to the first column of data. Okay. So pressure, you notice those are all the different column, the values of pressure. And then what we're going to do is I'm going to say, let's pull up data here. Then this is going to be tensile strength. We'll just call it strength. It's going to be equal to data in the column 2. 2. There we go. And you'll see now I've got a vector of all my tensile strengths. Okay. And each of those tensile strengths, that 225 corresponds to that value of 80. Right? So these are corresponding, exactly the same as any regression analysis. Now, in the function that we're going to do, ANOVA in, what it will do is it will automatically put a column of ones in and run the regression for us. So we don't have to put a column of ones in as if we were running the regress function. We're using ANOVA in. So the command structure for ANOVA in is p, comma, table, comma, stats. Okay, those are the outcomes that we're going to get. We're going to get the probability of rejecting the null hypothesis. We're going to get a table with lots of different statistics in it that we'll be able to use, including the sums of squares, including the F ratio and the probability. And we're going to get stats like we got in the regress function. Okay, same basic stats. All right, and what we're going to say is ANOVA in. Okay, that's analysis of variance, ANOVA in, with as many variables as I want. Okay, this is the general model. So we're going to now say we're regressing y on x, our dependent variable on the matrix of independent variables, and so it's going to be strength on pressure. Sorry. Okay, and later on we'll use this an array. So I put it in these braces. Okay, you don't have to do that now, but we will when we get even more variables in, and it becomes more complex. We're going to be using these braces to denote the independent variables. Okay, and then we're going to have this the way, and I'm going to put in what's called sum squares type. Okay, so this sum of squares type 2. Type 2 sum of squares is what we've been teaching you the entire class. It's a sequential sum of squares where they all add properly. It assumes homogeneity of variance and all those things that we've talked about. When we don't have homogeneity of variance, when we have non-orthogonality of our independent variables, right? Sometimes, when we have non-orthogonality, right, that's going to throw our regression equation off. And so we calculate the sum of squares types a little bit differently for those kinds of situations and when there's interactions among variables to account for that. And so there are several different types of sum of squares. For this class, however, we're only going to use the sequential sum of squares so that all adds and all the mathematics is going to be the same for you. And this is also the most commonly used sum of squares type. So make sure you specify that anytime you do an analysis. And then the last thing I'm going to do is specify alpha. A-L-P-H-A. And we'll just say 0.05 in this case. All right. We could change it to 0.10. We could change it to 0.03, whatever we want, right? We'll just specify 0.05. Okay. And then we can run it. All right. So we get a bunch of things. First thing that you see, of course, pops up is this table. All right. And we'll go through that, but I'm going to go in order. So the probability that we could have detected difference as large as we get of those pressures, excuse me, of the tensile strength given the pressure is about 0.08. So this probability that we could have rejected the null hypothesis is too high. So we're not going to reject the null hypothesis. Okay? So that's what P means. Table. Now we'll go to the table. Let's go to the table here. Here we go. Here's our table. And here we have, this is our variable. Okay, it's using the generic X. I could have put variable labels in and actually had this labeled as pressure. Okay, as pressure. And this gives us then the total sum of squares, the error sum of squares, and the sum of squares of our regression model. Okay, exactly the same as regression. So these will add. 15,000 plus 33,000 is about 48,000. Well, it's exactly, if I put all these together and add them all up, they're exactly that. Okay, within some floating point error, but these add. Sequential sum of squares add. Just like we showed you with the general linear model, with regression, sum of squares total is equal to the sum of the squares regression plus the sum of the squares residual. Sum of the squares total here is equal to the sum of the squares between groups, okay, the sum of the regression models between groups, plus the residual sum of squares, the error sum of squares. Those two added equals the total, always. Okay. they don't add up, then something's wonky. Okay. Degrees of freedom. Okay. Degrees of freedom for my groups. I had 6 groups, right? So 6 groups minus 1 is 5 degrees of freedom for the groups, grouping variable. Okay. The total degrees of freedom, I had 30 total measurements of the pressure and strength, right? 30 total. 30 minus 1 is 29. So 29 degrees of freedom total. 5 plus some number is going to be equal to 25 because the degrees of freedom have to add. And so 29 minus 5 is 24. There are 24 degrees of freedom in the error term. Okay? So these will all add. Sum of squares all add. Sum of squares divided by degrees of freedom. Remember, this is the numerator of a variance. This is the variability in our data of pressure, right? Excuse me, of strength related to pressure. The variability in that divided by its degrees of freedom gives me the mean of the sum of the squares, right? The mean squared error, and that is a variance, right? Sum of squares divided by degrees of freedom is a variance. We call those mean squares. Okay? The mean squared error, or the variance that's accounted for by groups. Okay? The variance, the mean square that's accounted for by our error, is the sum of squared error divided by its degrees of freedom. Okay? And if we account for more variance in our model between groups than we have error, okay, we can divide the mean square between groups divided by the mean square error, and we get an F ratio, okay, about 2.25. It means the variation we're able to explain in our model is about twice the variation we're not able to explain. Okay. Now we say we've got 6 groups. That's a lot of groups. They've got 30 total observations. So there's only what is it? 5 observations in each of those categories, and so it's very small sample sizes, right? And so we don't have a lot of power, and so that F at degrees of freedom of the numerator are the mean square divided by mean square between divided by mean square within is equal to F. So the degrees of freedom of the numerator is 5. The degrees of freedom for the denominator is 24. So if I look this up in a table at F of 5 degrees of freedom in the numerator and 24 degrees of freedom in the denominator, I would get a probability of about 0.0822. Okay, 0.0822, and this is higher than alpha. So our F is to the left, towards the center of the distribution, and so we're not going to reject the null hypothesis. So this is how to read an ANOVA table. You will be expected to know this and how to calculate all these things. Of course, Matlab will do the calculation for you, but you have to be able to explain it and tell me what these things mean. Remember, sum of squares add, degrees of freedom add. Sum of squares divided by degrees of freedom is equal to mean square. Mean square between groups divided by the mean square residual is equal to F. We can evaluate the calculated value of F, see what its probability is, and determine whether we reject the null hypothesis or not. Okay. Now we can take a look at stats. See all that stuff? That's the same stuff you get in the regress command, because what Matlab is doing is running the regress command in the background and then just organizing the calculations into the table. Okay. All right. We can look at the coefficients. Okay. These are our beta weights for every group, right? We can look at the coefficients. This is our regression model. This is our regression model. We can look at degrees of freedom error. Okay. We can look at the mean square error. That we've already seen that in the table. Okay. So it's taken a lot of these data and just organized it into a table for you. It's got a lot of things. It's got the means of the cells. It's got the different names of coefficients if I wanted to put those in. Some variable names so that you can have nice labels. Anyhow, so that's the stats command. The most important thing for that for you is to, if you want to look at the coefficients and to create the regression equation, then coefficients is the most important thing there. Everything else is included in the analysis of variance table. Okay, everything else is included in that. All right, so that's how to take a very simple set of data, okay, with multiple groups, and instead of running 5 choose 2, right, a lot of pairwise comparisons in order, what we do is we run one and we say that 0.08 means that none of those groups is significantly different from any other group, and we can stop. If we had found a significant difference, say this was 0.03, right, and our alpha was 0.05, we would reject the null hypothesis, and then we'd have to go start to look at those group means and start to see which ones are significantly different from each other. And that's called a multiple comparisons procedure, and we'll do that in our next tutorial. Okay, with that, I'm going to stop sharing, and we'll upload that. Have a great day.